Karelle Aiken, and I've been at Georgia Southern since 2007. And so today I'm going to tell you a little bit about the research that's going on in our lab. So I'm an organic chemist, and I actually have two main projects. One is like a reaction development called methodology, and the other one is a chemosensors project, which is more application. So today I'm going to tell you about the chemosensors project. So the title of this project is a 1,2,3-triazole chemosensors, all right? And we're going to talk about the synthesis and application of these molecules. Now this project is actually collaborative, and I'm working with Drs. Shanaz Lange, Debanjan, and Bosch here in the chemistry building as well, two other chemistry faculty. All right, so chemosensors. All right, this is actually a rapidly growing field, and actually you use it in everyday life already. So some sensor systems that you might know about are like diabetic test strips, pH sensors that you may use in general chemistry and other labs, and also pregnancy tests, right? Those are sort of sensing applications. So with what we're trying to do, we're trying to make organic molecules that you could potentially apply to like medicinal applications for like diagnostic purposes, or environmental applications, you know, maybe detecting some toxin in the environment. This field actually is very multidisciplinary, and of course, organic chemists are involved. You have a lot of analytical chemists, you have biologists, you have all sorts of scientists jumping in on it because we need everybody to kind of make things work. All right, so the basic idea of a chemosensor is this. We're trying to make a molecule when it's exposed to different substances in the environment, it can detect just one. So even with all those other substances all around it, we're hoping that our molecule will be able to, for example, if you look at this slide, be sensitive to just one of them, which, for example, would be the green diamonds that you see here. It would bind to the green diamonds and then somehow light up, give us some kind of signal that the green diamond is there in addition to everything else, but the green diamond is there. All right, so what kind of sensing signals are we looking for? We're looking for things like fluorescence or color changes. That's what our lab is focused on. Other people look for electrochemical changes as well, right? Or reactions. All right, so again, I told you we're doing 1,2,3-triazole chemosensors, and actually what you're seeing right now is a picture of a basic 1,2,3-triazole scaffold, right? Just the core of the molecule that we're trying to make. And other people have used it. There's a lot of precedents out there for this. They've used it in biological applications. They've used it in materials. They've used it in sensing small molecules. For us, in our lab, we're focusing on sensing ions. So things like cations or anions, right? And the scaffold is going to help us out. So why did we choose this scaffold? Well, for one, the chemistry that we're using, we call click chemistry. So that's what I have here on this slide. It's supposed to be pretty simple, high yielding, and very easy to do. All right, so it should be easy to make the scaffold, and if it's easy to make that 1,2,3-triazole scaffold, then it's going to be easy to modify it so that one, we can control the type of signaling that we're looking for. So in our case, fluorescence or color changes. And two, we can control the type of targets that we're detecting. All right, and so how are we going to do that? We're going to do that by modifying, for example, the units that are connected to our basic scaffold. All right, and so we're looking at maybe adding things like aromatic groups, extending that to control our color and fluorescent changes. And then we're also going to be looking at adding units we call functional groups. That's going to give us the selectivity that we want in detecting certain ions. All right? All right, so again, the basic chemistry that we're using is called a click chemistry. And in the click chemistry, you have the molecule shown here with the blue nitrogen, so we call it an azide, and you basically click it across an alkyne, which is the molecule we have shown here in black. All right, and again, you get your 1,2,3-triazole scaffold. Now, these are some of the molecules that we made in the lab. We have tons more going on, but these are only a few of them. And so what I'm going to do now is I'm going to show you some examples of what we've seen in terms of our detection. So again, remember, we're focusing on just cations and anion detection at this point. All right, so one of the first hits, one of the first successes that we had was a fluoride sensor. All right, and we affectionately call this fluoride sensor PTP. All right, if you come by my lab one day, I will tell you what it means exactly. All right, so PTP actually detects fluoride most strongly. It's also sensitive to some other ions, dihydrogen phosphate and acetate. But the strongest signaling that we get is with fluoride. And what happens is when you mix PTP with fluoride and shine a UV lamp on it, all right, you get this fluorescent response. All right, so when we first got this, we're like, well, what can you use it for, right? Because you think fluoride, you think healthy. But actually, an excess fluoride in an environment can actually cause bone deformity and also pitting of the teeth, right? So it can actually be bad for you. Also, people look at it in nuclear power for measuring uranium enrichment, all right? And then there are applications for like nerve agents where those things release fluoride as they're reacting, all right? So there are tons of applications out there. So some other sensors that we've got, just to show you some examples, are like with our copper sensor. And again, you can see we have the main scaffold right here. We're just changing the units on the outside, and all of a sudden, we can detect a different analyte. And so here, the sensor is clear just by itself, and we affectionately call this one BTP. All right, and then when you hit it with copper, you actually get a yellowy color, all right, signaling that copper is present. And then the third example I have for you, the last one, is what we call QPT, all right? Again, another nickname that we have in the lab, basic scaffold, just changing the groups on the outside again. You're getting different types of signalings for different cations. And in this case, this sensor is turning off, all right? So here it is by itself, nothing else, it fluoresces, but when it hits, for example, copper or iron 3, all right, it actually shuts down, all right? And we know those ions are present. So, where are we going from here? We're looking at tons of other sensors. I'm working with my collaborators. My lab is mainly responsible for the synthesis, and they do a lot of the analytical work. All right, so we can't just go by sight. And so the analytical work that they're doing, they're actually quantifying the signaling that we're seeing, all right? And once we can put numbers to it, we can say, yeah, for sure, our molecule is sensitive to one thing over the other. And some of the instrumentation that we use are NMR spectroscopy, absorption spectroscopy, and fluorescence spectroscopy. This would be UV vis, okay? And so that's where we are at the moment. But of course, all of this work cannot be done by just 3 faculty members. All right, we actually have students who are our workforce, who work very hard for us and get things going. And so we have undergraduate researchers in our lab and graduate researchers as well. And they're going to join me right now. And as you can see, I call them out of lab. They're actually very, very hard at work. So, or some of our undergraduate researchers are Mike, Nick, Sandra, and our graduate student right now is Richard. So it looks like they're hard at work, and I need to get back with them. So thank you for listening to us. Come by our lab sometime.